Last time we introduced the idea of the electric potential, and now we're going to look a bit more closely at how that's related to the electric fields. Just reviewing a little bit, we said that if we want to find the difference in potential, we can write that a few ways. We can write it as delta V or V sub BA, meaning the difference between the potential at location B and the potential at location A. Potential is defined as potential energy per unit charge, and thus we can get an expression like this. And eventually by plugging in force times distance over Q and substituting E for F over Q, we ended up with ED here, and we said that's only good if you have a constant electric field. If we don't have a constant electric field, we also mentioned you're going to have an integral. So here's our general expression relating the change in a potential energy to the conservative force that's related to that potential energy. So this works for spring forces and gravitational forces, and now it's also going to work for electric forces. If we divide each term in this equation by Q, each side of the equation by Q, then these U over Q's become V's and F over Q becomes E. So here is our general, most robust expression for the relationship between the difference in voltage, not just the voltage itself, and the electric field dotted with a displacement vector. So we could find this going along some line with a changing electric field and changing directions and some nasty, ugly integral. We could still find, if we had enough information, the difference in potential between two locations using this expression. Going back to the situation where we have constant electric fields, we're actually going to use this equation quite a lot because capacitors basically are built on this principle. So you should memorize it. And let's review this somewhat confusing situation of defining potential energy versus defining potential. So potential just depends on what's going on with the fields. So we have high potential on the positive side, whether it is a positive or negative test charge that we are concerned with, and low potential on the negative side. But what switches is the potential energy. A positive charge has high potential energy on the positive side and low on the negative, and that switches for a negative charge. It's got high potential energy over here, and over here it's going to have low potential energy, UE. All right. Hopefully that's starting to sink in a little bit. A quick little calculation: if we know the separation distance and the voltage between two parallel plates, and we want to use that to find the E field, we can use V equals ED, and we're just going to do the magnitudes for convenience here, not worry about the negative sign. So if you plug in 50 for your voltage, and you've got your distance of 5 centimeters, so that's 0.05, then you can solve for the electric field. It's going to come out to be 1,000, and the units here are volts per meter, and that is another unit for the electric field. We've also had our electric fields typically in newtons per coulomb, but that is equivalent to volts per meter, just another way of looking at an electric field. All right. Now we spent a lot of time looking at electric fields due to charged spheres. Now we're going to look at the electric potential. And to start off with, we want to know the potential outside of the sphere. It is a conducting sphere, so that tells us that all of the charge is on the surface of the sphere. And we know that the electric field outside of a conducting sphere is just like the electric field due to a point charge, so KQ, I'll do capital Q, over R squared. So if I want to find the difference in voltage, VB minus VA, that's going to be the integral of our electric field, and we'll say dr because that's what we're calling the distance element here, right? And there's a negative sign there as well. So all we have to do is plug in our expression for our electric field here, and K and Q are constant, so those guys can just come outside. There's our negative sign, and we've got the integral of 1 over R squared dr. If you haven't done that for a while, kind of the simplest way to think about that is the integral of r to the -2 power. So you're going to add 1 and then divide by -1, and so you're going to end up with r to the -r to the -1 power, or -1 over r, evaluated from a to b. That's what we're doing, right? From a to b. This is very good notation. I'm sure the math teachers would like this. So VB minus VA is equal to, and that negative sign will cancel with that one. So we've got KQ. That's not a Q, it's a theta. How did that happen? All right, KQ times quantity 1 over RB minus 1 over RA. So I'll draw that A there a little higher so it's not in the way. And as I mentioned in the previous video, you can set the potential energy for the electric potential equal to 0 at any location. And since V is U over Q, wherever U is 0, V is 0. So we can choose any of these locations to be 0 voltage as well. And what we typically do is we say, well, I'm going to set VB equal to 0 when RB is equal to infinity. So we're going to say 0 voltage is way out there. And if we do that, then these guys go away and our negative signs can cancel out. And we can get an expression for the voltage at any location. We can drop the A subscript is just equal to KQ over R. So there you go. That is part A. This is going to be an important solution that we're going to use quite a bit. Now if I want to find the potential at R equals R naught, well, that's simple enough because we've got our expression here, and this is true up until you are at the edge of your sphere, and R naught is right at the edge, so we can just plug that in for R and we are good. Now part C here, this is probably the most important thing. Pay close attention, take some good notes. Inside the sphere, you're going to want to say, well, I know the electric field inside the sphere is 0, so the potential must be 0. No, do not do that. If we look closely at our expression here, the electric field isn't related directly to the potential. It's related to the change in potential, right? This is another way of writing delta V. So it's not that V equals 0, if I plug in my 0 for my E here, it's that delta V equals 0. And if delta V cannot change, or V cannot change, that means it has to remain constant at the value that it was at the edge. So inside the sphere, it is still equal to the value that it had right on the outer edge of the sphere. It's constant, it does not change. Put some stars around this. Students tend to forget this one, but very important. 0 electric field means delta V is 0. Okay? Just to look at the graphs, our electric field is 0 inside, jumps up to some maximum value right on the edge, and then follows an inverse square law. The voltage is constant on the inside, equal to whatever the value is right here, where R equals R naught, and then it follows just an inverse trend, not an inverse square trend. Okay, so those are some important distinctions between electric fields and potentials. Another important distinction is that this guy is a vector. I mean, not the graph, but the electric field is a vector, whereas the potential is a scalar, and we will come back to that idea later. Alright, last example has to do with the breakdown of air, which is when it starts becoming a conductor, and that occurs at 3 million volts per meter when that is your electric field. Alright, so part A, we want to show that what's called the breakdown voltage, which varies from object to object, is related, it's proportional to the radius of a sphere, and then we want to do part B. So we just found that the E field due to outside of a sphere is KQ over R squared, and that the potential outside of a charged sphere is KQ over R. So we can see pretty easily that V equals R times E. And so there, we're done. All you have to do is multiply E times R, you get V. And so that tells you that the breakdown voltage is equal to this breakdown electric field, you could call it, this constant value here, times the radius of curvature of your spherical conductor. So if we apply this equation to spheres of a couple of different diameters, 15 centimeters and 1 millimeter, and look at the breakdown voltage for each of those, in the first case we're going to have V equals 0.15 over 2 because it's and that's diameter, and we want to make sure it's radius, times the breakdown electric field, 3 times 10 to the 6th. And this works out to be a big fat 225,000 volts. And then if we have a very small cylinder, so this would be like a needle point or something, where we're going to have 0.001, which is a millimeter, divided by 2 to make it a radius, also times 3 million. That's going to work out to be 1500 volts. So what does this mean? Well, it means if you're creating some electronic components that are going to have high voltages, you want to make sure that they're rounded and not sharp little pointy things, because then you're likely to get current to jump off. I guess we haven't used the term current yet, but electrons will jump off of pointed conductors a lot more easily than blunt rounded conductors. Essentially, a sphere with a 15 centimeter diameter can have a voltage up to 225,000 volts before you'll get arcing off through the air to something else, whereas a very pointy sphere, very small sphere, can only get up to 1500 volts before you'll get some arcing to the surroundings. Okay, catch you next time.